And here we are. I think we're on live.
Right.
Okay. Yeah, perfect. Hey,
We're live.
everybody. Yeah, thanks
Hi.
everybody for joining. This is the first public version of the ACV meetup by Biped. We're very happy that you're here, and we are even more happy that Thibault volunteered to give us a great talk about real-time practical monocular 3D perception through spatio-temporal consistency. And I would say I will just leave the stage to you, Thibault, to introduce the topic, and have fun.
Great. Thanks a lot, and thanks for everyone to joining this presentation. I am Thibault Neveu, the CTO at Visual Behavior. We're working on robotics perceptions. So our goal is to give robots some kind of scene understanding that they can use to perform action, doing motion planning and controls, and so on, using only cameras, so that we can scale properly. So I'm going to try to introduce you how we work on monocular 3D perceptions, so using only one camera, and how we use different kind of inductive bias to make it so that our models can run faster. So I'm going to introduce six pathways that we use and stick to the end because the fourth one is really impressive. Okay, so I'm just going to start to show you basically what monocular perception is. So this is one demonstration that we did at the CES 1 month ago. So what we can see is a racing car that is following someone. And what we see, if I play stop, pause, what we can see there is on the upper right corner, the monocular perception that is embedded onto a Jetson. And we have the floor, which is detected. So this is all the drivable area. And we have here the near obstacles in front of the car. So that was one small presentation that we did. Also, I don't know how you work with the question, if we wait until the end, or
I guess how you prefer.
Yeah, gradually. So as soon as there's one question, everybody can just jump in.
Yeah, okay, could be great doing like this. Okay, so that was basically an introduction of what monocular perception is embedded onto a Jetson. Okay, we move on. So on this demonstration, it was running on the Jetson Xavier. It was running at 40 FPS with roughly 358 pixels per 358 images. And so we're currently working to make those kind of models to work even on smaller hardware, like, for example, the Jetson Nano. And we expect that we can probably reach something like 10 FPS using a variety of methods that I will introduce in this presentation. Okay, so just to go back to the basics, so that we can understand properly the concepts I will talk after, is asking the questions about how mammal, so in general, is not only human being, but all mammals perceive the depth and scene understanding around. So there is a lot of different mechanisms that we as human beings use and also mammals use to perceive depth. The first one that is usually leveraged by stereo camera is stereo, the fact that we have two eyes. And so by using the disparity between the two eyes, we can have a feeling of how far or how close something is from the camera. That's one very common thing, but sometimes in robotics, it can be a struggle to work with that because you have to be sure that your lens will always align properly. And if at some point, it's warming, or maybe after 1 or 2 years, your lens can slightly move. And if it happens, then your robot is messed up, but you can't rely on stereo anymore. So that's sometimes one of the struggle people have with stereo camera. Then there is the semantic world of just trying to perceive depth using only semantic informations. So using color, blur, textures, perspective. This is a bunch of clues that we can use to know the depth into an image. And this is what those monocular networks use. Then there is some other concepts that we use as optical expansion. This is this notion of if something is moving very fast in front of you in the axis, so in that direction, if you see something coming, or if you're walking and you have, for example, a wall in front of you, optical expansion is the process by which you will rely on optical flow to measure how fast something is coming to you. This is sometimes also referred to as time to contact, so the time for an object to hit the camera. And this is something very interesting to use because it do not need multiple cameras. The only thing you need is one camera and having some kind of motion that you can leverage so that you can deduce in how many times these things will hit your camera. Then you have this notion of parallax. So this is like if I move like this and I look at my scene, even though I have only one eye, I can still try to see how does the world behave. By using this parallax, I will know if something is very far because it will not move a lot from my perspective. But if something is very close, it's going to move a lot when I'm going to move like this. So by using these facts, you can know how far something is. You have saccadic attention, so you can try to refer to different points in the image. Motion blur, I'm not going to go too much into the details, but if you move very fast into one direction, the blur that you see in the image is proportional to the distance of the points. So how to perceive depth with one eye? So most of the stuff that we see, I mean, the most popular models when we talk about monocular perception rely on semantic information. So they leverage, so they can't use stereo. Most of the times they use semantics and semantic clues like color, blur, texture, and perspective to deduce how far something is. Yeah, someone just jump in. Okay. So one of the state-of-the-art monocular depth perception models is vision transformers for dense prediction. Maybe this is not the state-of-the-art right now because it moved so quickly that maybe this is not anymore. I don't know. But I mean, a few months back, it was the state-of-the-art. So these models rely only on semantic. So you have one image and they use some kind of embedding like the VIT model is doing with transformers. And then they pass that to some VIT blocks, transformers, and they predict depth informations. And what they show is by relying on transformers, they can have more precise and dense information, more accurate information on depth map. They also have an hybrid models when they use both a ResNet model for the backbone and for the transformers with VIT blocks on top of that to predict depth information. So I'm gonna try to give you some insight about what's wrong with these models. So there is many things that make it so that we can't use it as it is to go in production. The first thing is the way that they train the models. What they do is that they train a loss with inverse depth. So not bad up to now. But what they do is that they try to normalize the ground truth. So the normalization is made as such that you will try to get rid of the scale and the shift of the scene. So what it means is that what the model is predicting is the inverse depth with up to scale and shift ambiguity. So if you use that with a robot, it means that, well, you know that's how things are relative to each other, but you don't know exactly in an absolute manner how far they are from your robots. So in some cases, it can be useful, but if you're doing things like obstacle avoidance or other kind of stuff, it can very get tricky. Because at the end, when you're going to use your model at inference, it means that the predicted depth that you will use have to, if you really want depth information, you have to rely on some scale and shift that you don't know. You don't know those things. You can know them if you have a LiDAR, for example, just next to your camera, or you have some external information to guide you. But if you just use one monocular camera, you will just don't know those kind of information. So the main issue, if I try to summarize, is that you don't know the scale and the shift. The model can be slow. I mean, even the hybrid models, there is a ResNet plus VIT blocks, and that can be extremely slow to run on the Jetson or some embedded hardware. And you have a lack of temporal consistency. So it means that the scale and shift that the model is providing will not be constant. So on each frame, you're not guarantee that you will have a consistent eye depth, because the scale can vary a lot, and so it can make extremely hard to use those kind of information if you want to do mapping or localization with the depth that is provided by the model. So if we try to take a step back and try to think about how we can go from monocular depth perception from research to production, there is a lot of things to improve, but also a lot of method that we can try to rely on. So instead of relying only on semantic, we can try to leverage all the other mechanisms that we use as human beings to perceive a scene, which is optical flow, parallax, saccadic attention, motion blur, and consistent temporal prior. And we can try to optimize this architecture so that the backbone and the VIT blocks can run faster on embedded hardware. Is there maybe some question before I jump into? Nope. Okay, so first, one of the first methods that we use to make that networks to go faster is to use what we call guided attention. So the VIT blocks rely on attention mechanisms. So we much into the details. What they do is that they try to patch, to create a series of patch on the image. And what they do is that for each query, they try to do the dot product. So they create an attention mask that they can use to aggregate the value from the networks. And by doing so, this is why attention sometimes I refer to be better or sometimes good to put at the end after some convolution, is because you can have this global context and you can dynamically choose the kernel values on how you're going to aggregate the values. But the thing is, if you do that for all your layers, if you're running the attention for all your layers, this operation, the query, when you do the dot products between the query and the key, that operation is extremely costly. This is something like 33% of the attention block is made by this part. So what we do is that we use instead with the guided attention. So this is one thing that we can use is that instead of computing each time at each layer an attention, so a dot product between the query and the key, what you can do is to optimize that process so that we do not each time compute that things, but we rely on the previous dot products in the previous layers. So by doing so, you still leverage the dynamic kernel attention made by transformers, but you try to more efficiently reuse this type of information in the multiple layers that you use.
Yeah. Can I ask one question?
Yeah.
This attention is this is not over time, right? This is only the attention inside the one input image.
Exactly. Like in the architecture, you have multiple blocks.
Yeah.
So multiple attention blocks as well. And so what you want to do is to compute as less query time query as possible. And so you try to reuse the previous one.
Yeah. And just out of curiosity, because it just comes to my mind, I'm not sure if it makes a lot of sense, but did you try to just do it, like see what is the difference between doing it very early in the network to have a bit cheaper attention? Why? Because the
what the networks do is that it's really doing different kernel attention at each layer. But if we force the networks to come up with fewer kernel attentions, it will try to find a way to make it more efficient, since you're not gonna lose a lot of accuracy at the end.
Okay, so reducing the amount of attention blocks, so to say, is actually like a positive thing or like a equally good thing.
It's like closely equal, almost equal things. Yeah, exactly. And what you can vary, the parameters that you change is on how many attention blocks you compute again your attention kernel.
Okay, thank you.
So just to say, that is one way that we can optimize the attention mechanisms. But there is a myriad of papers that show how we can leverage better attention without relying on doing the dot product between all the key and query pairs. So that is one thing that we can do, but there is a lot of others. So, but that's one avenue. The second one is to use efficient depth refinements. So as I mentioned, we have multiple VIT blocks. And what is going to happen is that for each new block, we are going to compute a new value for each part of the image each time, no matter if this value is already good or not. And it comes at cost. Like I made, so here is one example to show that on the left here. Like the depth, maybe after the first VIT block. So this is very rough example. Of course, this is not a realistic one. But what could happen is that you have some value that already converge towards a good value, a proper one. But some other value might need some more computation so that they can run more effectively, so that they can be more accurate. And so instead of computing the attention on, like instead of updating each token, you will try to filter out the tokens that you will use at the next block, so that's your model which only makes the refinements on the part of the image that have to move forward. And what you do to know which key to select, you will ask the network to predict for each token, am I done, or can I still improve that part of the image? So this is where I illustrate on the middle here is that for those part of the image, we still need to improve. So the only part where we're gonna update, we're gonna run our attention are gonna be on those parts. And this is what we call here the refine guided attention, where we filter exactly the value that we're gonna update, as well as which dot product we rely on. Which kind of makes sense, and it's come back as well on this idea of cyclic attention. We have this potential as human being where we move our eyes to carry some information from one part of the image. And if we know that something is far away and we don't care about it, we don't have to look again at that part of the image. We don't care about it. But if something is very close and we want to be more accurate, like maybe we want to do that for obstacle avoidance, for example, in robotics, then it's becoming very important to maybe look more on that part of the image instead of updating everything. And so by doing so, we can extremely reduce the computational efficiency of the model as we progress into the VIT blocks. Does it make sense?
Yes.
Great. So that was the second avenue. Let's move to the third one, is to introduce this recurrent formulation. So let's say we have here a static scene and we are moving the camera in the scene. So there is a prior that the scene is constant, of course. I mean, there is some kind of consistency in the scene, which might be true in the robotics context. If we do that, the camera might be moving on this picture from here to here, like that. But what it means is that the networks at time t+1 already compute most of the information that we have into the image. Like there is not a lot of novelty into the image. This is mostly the same thing. There is just some new information that pop in on the top, but we can leverage a lot from the previous information that we already have to deduce what's here. And we just have maybe to compute here at the top of the hairs that might need slightly more computation. So if we mix this recurrent formulation with the previous point just before, it means that the networks can use most of the information that you already computed before and leverage that information to just compute the new information that come into the image and make some refinements. This is why also, like when you go from step t+1, from step t to step t+1, you have to transform somehow the representation that you have to a new representation. You can do that in two ways. The first one, you can do it manually. Like if you have a robot and you know somehow how is the ego motion of the robot, you can manually transform your feature map or your representation of the world so that it's gonna be more close from what is should happen into that world. Or you can let the network decide how to transform that information, or you can do both at the same time. And so these things is not really interesting when you not use the second point that I mentioned before, these points. But if you use it in combination with the second one, you can get a lot of value and a huge improvement.
Can I ask a question here as well?
Yeah.
So basically the idea would be that when you say we know let's say, given we know the perfect motion due to some other sensors of our robot or whatever films,
Yeah.
when you talk about shifting the feature map, where would that happen in the whole pipeline? Would it happen before, inside, or the network?
So the transformers has those positional encoding that
Yeah.
gives the network some kind of information about the location of the token.
Okay.
So if you know that you are sliding like this, you can slide all your positional embedding so that the network will know that the position is no different. And you can then let the network decide on what was the good transformation to do.
Okay, and when you talk about learning this transformation or this slide or shift,
Yeah.
what kind of data do you rely on to learn that? So you would have like ground truth data that would actually give you.
Yeah, you have to rely on video data sets. So I mean, it depends of the context, but there is a lot of either real data sets or synthetic data sets that give a lot of different length sequences on which we can rely on.
But do you need you also need the positional data for those video data sets?
If you have it, that's better. If you don't, the network will learn it by itself. That's why it can be a two-way, like you have two pathways. The network can learn it, or you can strongly give that prior to the model.
But how would it learn the shift? By just predicting how it would look in the next frame, and then you compute the loss between that? Or
exactly. I mean, if you ask your network to come up with a transformation that will transform and shift all the embedding, and you have a loss at the end, the only way for the network is to deduce this transformation.
Cool. No, I mean, this makes total sense. That
I mean, from a human perspective, it makes a lot of sense, since this is exactly what we do. We only update our representation. We don't compute everything each time again, and well, that's why it's extremely powerful to do that kind of thing.
Cool.
Okay. So just an intermediate summary of what we have talked about up to now. We have focused basically on how to reduce the computation of this variety block. That was one of the main things that was taking time on our models. That was not the only one. Like the ResNet can be packaged very efficiently, but there is still a lot of things that we can improve on this backbone. Like maybe we don't need a ResNet. Maybe if we rely on a smaller network, like a mobile net, we can go even faster when we're going in real time. But if we rely on the smaller network, of course, we're going to lose a lot of performance. We're not going to be as good as for predicting depth with only one image. But the main reason is that using only semantic to learn depth perception is extremely hard. I mean, as human beings, we rely on so many things to get depth information. Here we have a network to rely only on the color value, blur, texture, and perspective, and so on. So if we reduce the backbone, we have to leverage some other mechanisms as well, so that the network can have less to do on the backbone, but so that it can rely on other mechanisms to compensate for this lack of parameters. So one way that we can try to, by using only monocular perception, we can try to get depth information is by using what we call optical expansion. So here is, so I just listed one paper that is doing that. There is not a lot of paper doing that, by the way. It's upgrading optical flow to 3D sense flow through optical expansion. So what this paper is doing is that it's using optical flow. So this is the motion of each pixel in the scene. And from optical flow, what you can do is to deduce an optical expansion which is from one particular location in the image. Does its part is scaling like this, or does it scaling like this? And if you know how does each part of the image scale, you can then deduce depth information. In this paper, they're deducing 3D sense flow, but from 3D sense flow, you can have depth information as well. So yeah, so this mechanism, you can only rely on this mechanism if you have a move on your axis, on the main axis, like here. If you're moving in the lateral movement like this, you can't rely on your optical expansion. You can only use optical expansion if you're moving in front of you. So that's one way we can get depth. Another way is to use motion parallax. So this is the other way, like optical expansion give you depth if you go in that direction, but if you go in lateral direction, if you use motion parallax, and it's like kind of the same thing as using a stereo setup. Like you have two lens close together, and so you have a baseline between those two depths. And if you get disparity, so you get the matching between one lens and another one, then you can deduce depth. Motion parallax is the same thing, but the difference is that your first camera is time t, your second camera is time t plus 1, and you might not be perfectly aligned. You might be like this instead, or you might be like this, or maybe you can be like this. But what matters is the disparity between the two images. And if you get this disparity, then you can get depth information. So what you have to rely on is on the ego motion of your robot, if you have some kind of ego motion. And if you deduce this disparity, it's like a so-called epipolar geometry. It's relying on the epipolar geometry to do that. And if you do that, then you have disparity and you have depth information if you move in that direction. So now we have two mechanisms, optical inspection and motion parallax, that we can use to deduce depth when we move into the scene or when something is moving in front of us. And what great things is that when we rely on those two type of mechanisms, we can solve the ambiguity that we had before with the scale and shift, because now we have some information about, it's like ground truth, because I mean not ground truth, but like real world information about how does the scene is scale and shift properly. And so the prediction that was coming from the monocular model that would rely only on semantics can now be updated so that we can get a real prediction that we can use in real time. And one thing I do not mention here is that because so now we can reduce the size of the backbone, because we can also give new information to the networks that are coming from the optical expansion and from the parallax, so that the network can have already some prior about how the scene is made and can just basically update the scene to make it more usable in real world situations, to make regulation on some part of the image, and we can then solve this scale and shift ambiguity. Now we have a model that is fully optimized, and we hope that we can run it in production properly. Well, that's the end.
Perfect. Thank you very much. Yeah, any questions, remarks, ideas, so on? Otherwise, I can do some, but I think I already asked some questions.
I do have some questions.
Perfect.
That was a very good presentation. Thank you very much. And for me, it's really nice because I don't have a lot of experience with 3D, and I want to get in this field. That's why I joined the meeting. But one question that I have, when you're talking about monocular depth, can you retrieve the depth map only from one image, or you always need a video to retrieve the depth map? So structure for motion, for example.
So
if you have one image, you retrieve the depth map.
So motion parallax, I was talking here, is depth from motion. So you have to use two images. So that's based on those two images, and using epipolar geometry, you can then retrieve the depth. The network I was talking at the beginning, the one based on transformers, this one was relying only on one image. That was a backbone of VIT blocks only with one image, and this is why you can't know the scale and the shift of the scene. You have some ambiguity.
Exactly. So if I have a problem where I need to have the real distance with just one image, it's not possible, right? So that's simple.
No, with only one image, you need some external prior about the world so that you can deduce the size or the distance of the objects. Like one way you can do it is to have a very strong prior on the object that you're looking. Like let's say you are on the road, you're doing an ADAS system for autonomous vehicles. well, if you see a vehicle and you know roughly the size of the vehicle, and you know the distance, I mean, you see how big the object is, then you can know the real depth. But this is relying a lot on semantic, and so this is very specific to one given distribution of data. So if you want to be agnostic to the distribution or be more general, then you need some external prior.
Nice. Thank you. That was very helpful. Yeah.
Okay, I will start. I have some. I mean, thank you again for the presentation. Really liked it. Also liked how you went over like some ideas. Okay, how when we go from research where we could go further. I have some questions more regarding to the hardware side. So at the beginning, you said on the smaller Jetson board. Maybe you can just open this slide again. You can go up to 10, like the Nano, where you say it's work in progress. Do you use, apart from quantization, do you use any other techniques to make it work, or do you even use quantization?
We already use quantization. So the thing that you see on the left do not use quantization. So there is still room for improvements on that one, especially on the ResNet architectures. Like the time when we tried quantization, we had a network with a lot of back and forth, with a lot of outputs, and going from quantized to float 16, a lot of time were kind of consuming a lot, and so it was roughly the same as running the networks without quantization, only with float 16.
Okay. And like, I was wondering, do you have maybe you have a rough guess on how much like the results suffer from the step to quantization? I mean, obviously, I think they will get a bit worse at least. Would you say you have a guess on how much that is?
I think what we have to care about when we do those kind of analysis is the metrics that we use to see how much we lose. Because if you lose a lot of accuracy for objects that are very far away from you, you don't really care. What you really want to be sure about is that you keep a lot of accuracy for the things that are in front of you and that you really have to avoid or be sure about. And so if you train your neural network in a good manner, you can maximize the performance of the models on those parts, and therefore when you're gonna run the quantization, you can keep a very good accuracy on those parts of the image while losing some information on some others. But you can have a good balance between both.
That's totally something we've encountered as well, as when we tried different models and we like played around with different architectures, is that when you just look at the raw for example, MAP score, that it might be quite misleading if you don't check the results itself, because then it's some like cars which are like 50 meters away, which are not correctly detected, but the ones that are actually important, as you mentioned, are. And then I was wondering, so as you mentioned, you train it on video data. Do you have also a private data set or data set within your company, or do you think like for your task the publicly available data sets, like I don't know, YouTube VOS, and there might be the Kitty ones you use, are enough?
We have both. Like we have public data sets, but we're also working in a partnership with other companies that provide some other data sets that they have, so we mix both at the end.
Okay. And then those,
but I guess that you can get 90 to 95% of the performance just by using publicly available data sets.
Okay, I was wondering whether.
Okay.
Thank you.
I was also wondering about the kind of working range, because I mean, stereo cameras typically have a working range where they say the precision at, for example, 2 centimeters is max 5, 6, 8 meters, depending on the size of the camera. And for the very small ones, for example, that we embed from the Intel RealSense ones, we're looking at maybe a 6 meters range where we have a good precision. If like there is on the kind of applications you're using, what kind of distances are you talking about? And is there a way to think of it as a way to expand the performance when we look at further objects?
Yeah, so that's a great question. So there's two ways to answer. let me go back. Yeah, here. So the first one, which is not this one, this is the semantic models. If you rely on semantics, the semantic is gonna try to make something looks great. So even though you're not gonna be good far away, you're gonna be kind of consistent. That's the first thing. I mean, it's gonna looks okay, even though everything will not be correct. For stereo camera, if you want to see further away, you want to increase the baseline. Like if you have a small baseline, you're gonna see very close to you, but not further away. If you have a huge baseline, you're gonna see a lot far away. That's why self-driving cars use baseline, because they want to see vehicles 30 or 40 meters away. So if you use motion parallax, it all depends of how your robot is moving and which keyframe do you use. If your robot is moving in that direction, let's say this movement, so you have some kind of baseline to use. So the question is, do you run the motion parallax model every 2 millisecond? So the baseline is going to be extremely short, so you're not going to see extremely far away. But if you use a good baseline, you can improve the precision for far away objects, because you have virtually increased your baseline. Does it make sense?
Yeah, it does perfectly. Yeah. And another question that I had was regarding the kind of backbone architecture that you're using in your experiments.
Yeah.
I was curious, like whether you've tried like the recent YOLO V5 ones, or if you're onto a bit lighter ones. Like what's usually your go-to? I mean, for things you can disclose, but what's your go-to approach if you?
Well, we try most of the. I mean, what's great thing about opening models on GitHub is that we can very easily switch from one backbone to another. So we do not run a lot of experiments on which model is which backbone is the best. So we use ResNet as the baseline, and then when we have to run more efficiently, then we use EfficientNet or MobileNet, for example.
Okay. Okay.
But on our side, this is really not a lot of works to switch from one to another.
Yeah, and maybe then one final question regarding the kind of applications that you have at Visual Behavior. What kind of constraints do you have? Sometimes I guess might be like size of the embedded hardware or anything that would make you go for monocular depth estimation rather than playing around with a stereo camera. Where would the constraints come from? Is it like from the customer level, or is it on your side?
Yeah, from the way that we see vision at Visual Behavior, on why we are doing those type of architecture, is that we think that one way of getting good results for high-level robotics application is to get a scene representation that we can use to go onto those high-level skills. Like if you have one network for predicting objects, one network for predicting depth, and you try to mix all of those to get a good tracker, for example, let's say, well, you're gonna have good results, and it's gonna be a lot correlated with the efficiency of your detector models and your depth. But the network doesn't have the ability to fuse that information itself. So the way that we move forward is by trying to mix all those information. So that this is why I was listing all the things that we do as human beings to perceive a scene, because by mixing all of that, we can create a coherent representation of the worlds, and we can leverage that representation to access high-level world understanding, or predicting objects and so on, building occupancy map for robotics, those kind of application.
Okay. And sorry if I may, one final question on the kind of approaches that companies, for example, like I don't know if you're familiar with Coma.ai. Yeah, like the kind of self-supervised approach where I guess there is no explicit moment where they compute a depth map for obstacle detection. I just want to get your...
I mean, the way Coma is doing is by going directly from the perception, from the raw image information to the action. Yeah. So there is nothing there is almost nothing in the middle. This is going from the raw data to the actions. Yeah. So we do not exactly do that, since what we do is that we create this representation and we try to maximize the performance of that representation so that we can use it for various applications. So that's how we differ from Comma AI in the approach that we do in computer vision. So we are more closely related with the way that Tesla is doing with their cameras, because they have really a different pipeline between the perception and the motion control and action. They have different things. This is two separate things for them, because they first build that representation with all the cameras, and then they use that representation to perform the motion planning and the control.
Yeah, okay. So the scope really of visual behavior is to try to keep that high-level representation as consistent as and complete as possible, and then you have a couple of downstream tasks. It's not like, okay, no, got it.
Exactly.
Thank you very much for the answers.
To piggyback on the like using the small baseline to have a good accuracy close range, and then a bigger one to have a better one, a further range. Could you combine those two? Where you would take three shots at 3 different timestamps to being super close, and then a further one away as the robot is moving away to have like good accuracy.
So you can do 2 different things. You can, as you said, combine different keyframe, one close and one further away, but you can also combine motion parallax with semantic plus optical expansion, because optical expansion is if you have something that is coming into you, which is what you care about, optical expansion would be very good for that, for detecting those things. So by having a huge baseline, you will miss the opportunity to see things close to you, but optical expansion and semantic can take care of doing those things.
Thank you. Thank you for the talk.
Thanks.
I was also wondering if you had, this is the path that you've taken that worked in the end. Do you have any other, I'm sure you had to explore a lot of different approaches. Is there any that you tried and you had a lot of hope in it, and in the end it didn't work out, and you had to find another clever way?
It's more, but I mean, there is a lot of things that we tried that did not work at all, for sure. But it was most on how, I mean, what I introduced here was the high level information about how we can leverage multiple mechanisms. Those mechanisms, we know that those mechanisms exist, and we know that this is great mechanisms to use. The question is how exactly to use it. So we did not have one mechanism that we have selected, and we realized that it was not the good one, but we had a lot of struggle on using these mechanisms and finding the way that we can use this mechanism and mix this mechanism with other mechanisms so that we can get good depth information. And here we tried a lot of things and we failed on a lot of different things.
Yeah, well, I think that's normal when you try to innovate.
Yeah.
Thank you for the answer.
Thanks.
Okay, if there are no more questions, anybody? No, I think then I can just finalize here. Thanks again to you, Thibault. Great presentation, really good insights. Very
Thanks
happy
a lot
to have you here
and for your question.
Yeah, and just as a little look up for you all for the future, we're gonna continue with this series. The plan is to do it once a month, and we already have a next talk which will go a bit more. Paul is also here. Yeah, the one checking. It will be a bit different. It will be about how we can maybe substitute at one point neural networks or maybe even vision transformers with a more physical approach, but I'm not going to spoil it too much here. And I'm going to send around more information about that. And this next talk will be on the 9th of March at the same time. So if you want to get updates and stay in touch, just sign up on the website. And yeah, thank you very much again. And I wish you all a great evening.
Thanks a lot.